Hello, and welcome to the lecture on Chapter 7 on the topic of Earth. This is the first of a series of lectures that are going to cover the planets in our solar system, starting with our own home planet. Okay, so we're going to have a quick overview section, just talking about the overall structure of the planet. Then we're going to get into the details. We're going to talk about Earth's atmosphere, its interior, and the surface. We'll also talk about the magnetosphere, which is above the atmosphere, also penetrates the atmosphere, but it's the biggest structure. And we'll talk about Earth's interaction with its moon that creates the tides. All right, so let's get to the overall structure. So a good way to think about Earth is like an onion with different layers. There is the mantle, which we can see up here, okay? There is the crust as well, which sits on top of the mantle. We'll talk about that when we talk about plate tectonics. Okay, there's a thin crust. There's a two-part core, okay, with an outer core and an inner core. All right. There are the oceans on top of the crust. There is the atmosphere, and then shown here as just kind of a vague idea, somewhere outside of the planet is the magnetosphere. Magneto obviously referring to a magnet. Okay, it's our magnetic field is the magnetosphere. All right. Okay, so what about Earth's atmosphere as we get into the details of the planet? Well, there's some really interesting details about the atmosphere. So if you look at this diagram here, we have on the vertical axis altitude. So starting at sea level, going all the way up to 100 kilometers above sea level, where you get into what's considered outer space. And then on the horizontal axis, we have temperature. That's just how hot the atmosphere is. So notice this blue line, the blue curve. It shows the temperature as altitude goes up. Now you might expect that the temperature should just fall with altitude. As you go up to the top of mountains, it becomes very cold as the atmosphere becomes thin. But there's more to it than that. We see that within the weather zone, indeed, the temperature does fall as we go up in altitude. So we see the temperature decreases as we go up. But once we get into the stratosphere, the temperature actually increases again, okay? Now at this point in the stratosphere, this is above 10 kilometers, this is a very thin atmosphere that you would not be able to breathe. And you would not necessarily feel this high temperature because there's so few molecules that although the molecules have high temperature, there would not be a lot of heat. But regardless, the temperature does go up. And that's because of the absorption of certain types of electromagnetic radiation that is occurring in the stratosphere. As we move into the mesosphere, the temperature falls again. But in the ionosphere, the temperature actually increases, again, due to absorption of electromagnetic radiation, in particular X-rays in that very upper atmosphere. Okay? All right. And a note, the troposphere is where convection takes place. All right. So what's going on with convection in the atmosphere? Well, that's what drives the weather. That is hot air rising and cool air sinking. That creates big structures called convection structures or convection cells within the atmosphere. Moving on to some details about the ionosphere. This is where we have the ionized molecules by solar radiation, the aforementioned electromagnetic radiation. All right. It reflects radio waves in the AM range, but does allow for transparent passing of FM and TV rays. The ozone layer is between the ionosphere and the mesosphere, and that's where you have a lot of absorption of ultraviolet radiation. Because although some ultraviolet radiation does make it to the surface of Earth and is associated, rightfully so, with things like sunburns, there is a lot of ultraviolet radiation that is absorbed in the atmosphere, which is good because if there was as much coming to the surface as is in outer space, then it would not be good for life. There'd be too much random mutation, too much cellular damage on an average scale for surface life to certainly reach the complexity level of multicellular life forms like ourselves. Okay? So one thing to consider are CFCs. Maybe you've heard of these in the context of global warming and concerns about humans' impact on our atmosphere. CFCs stand for chlorofluorocarbons, and they have been damaging the ozone layer, all right? And they have resulted in an ozone hole shown here above Antarctica, all right? At the center of the ozone hole above Antarctica, okay? Okay, so what does Earth's atmosphere do? Well, it is very important for surface heating. How so? Well, sunlight that is not reflected is absorbed by Earth's surface, warming it. Okay? Because the surface of the planet is not completely reflective. It's not like a mirror, certainly. It's not even like snow. If the planet was covered in snow, it would be a lot more reflective. But there are many parts of Earth's surface that are rather absorptive. Think of darker colors as being better at absorbing light. Well, as the surface warms up, it re-emits that light as thermal radiation. We discussed this when we talked about the ideas of light and electromagnetic radiation. Things that vibrate, molecules that vibrate at temperatures in the range of about 300 Kelvin, consider the figure before, and that's going to be kind of room temperature. Well, then, in that range, about 290, all right, Kelvin. But regardless, thermal radiation is then going to be emitted in that infrared, right? That's what you'd see with heat vision, right? Okay, but that light, that very invisible to human eye light, the thermal radiation, the infrared, it gets absorbed by the atmosphere, which causes further heating. So the atmosphere acts like a blanket, trapping that infrared light, which is so important because otherwise that energy associated with the infrared light would just leak back into space. Even if the surface warmed up, it would just lose that heat back into space. But the atmosphere prevents that heat from being lost back into space, causing further heating, which is good for surface heating. Okay? All right, that process is known as the greenhouse effect. Why is it named the greenhouse effect? Because it's exactly what happens in a greenhouse. Because glass is transparent to visible light, but opaque or not transparent to infrared, just like the atmosphere. Just like the atmosphere. See, the atmosphere doesn't let the infrared light escape, it absorbs it. Glass does the same thing. That's why you can make a greenhouse out of glass. All right, so it is a very apt name. Obviously, our atmosphere is not made out of glass, but the physical consequence of glass being not transparent infrared light and our own atmosphere being non-transparent infrared light is absolutely a good way to compare the two phenomena. Okay? All right, so there we have the greenhouse effect, that ability to allow for passing of visible light, but no passing of infrared. It's simply that criteria. Okay? So as far as a very good question that every 5-year-old asks, why is the sky blue? Well, it has to do with scattering. So scattering of light by air depends on the wavelength of the light. So different wavelengths are going to scatter differently depending on the molecules they interact with. Okay? Well, it turns out that the wavelength of blue light is closer to the size of air molecules. And that allows that particular wavelength light to get scattered readily. That means that light is getting bounced in every direction. So when you observe the sky looking up, you're seeing that light that is bouncing in every direction. The light that's coming straight through, the longer wavelength red light and green light and so on, you don't see it because it didn't get bounced around. It's coming down and it's getting absorbed by materials that might appear black. It's getting reflected by materials that might appear red. All right. So the idea is that you just are seeing the scattering of blue light due to the similarity in the wavelength of blue being similar to the size of the molecules. Okay, that's the scattering that makes the sky blue. So, why are sunsets red? Well, when the sun is close to the horizon, the scattering by dust in the air makes it so that so much of the blue light is scattered that only the red light is left, and you see that red glow. Because at that point, the blue light has been scattered so completely that you're not seeing it. You're not seeing the blue light, and only the red light is making it to you. So you're seeing the light that's able to transmit through the much thicker atmosphere at sunset. Not because the atmosphere changes during different times of the day, but the path of the light has to pass through a thicker amount of atmosphere. It simply comes down to the fact that during the day, when the sun is directly overhead, the light passes straight through the atmosphere. At sunset, when the sun is like this, it has to pass through a much thicker amount of atmosphere. See how much thicker that is? Okay? All right. So the history of Earth's atmosphere. How did we get it? Why does our planet have an atmosphere? When we talk about other planets, we'll talk about planets that don't have atmospheres. Well, the primary atmosphere was hydrogen, helium, and this escaped Earth's gravity because these very small atoms of hydrogen and helium, the smallest atoms of the building blocks of the universe, are very easy to accelerate, very easy to pick up a lot of kinetic energy and velocity. And so they're able to gradually escape Earth's gravity, okay? But a secondary atmosphere formed from volcanic activity. This one was mostly nitrogen. Well, life appeared, creating atmospheric oxygen. So now we have an atmosphere that does have some hydrogen in it, but is mostly nitrogen and some oxygen. And those larger atoms of nitrogen and oxygen and the molecules they form aren't easily able to escape Earth's gravity because they're more massive and don't pick up as much speed. Okay? So one result of modern society, and this has to do with global warming, has been to increase the amount of CO2 levels in the atmosphere. A corresponding increase in the global average temperature has been seen as well. Absolute data there. So exactly how much the temperature will continue to increase is not known, but we have lots of models and as we continue to collect data. So some possible consequences of global warming are that as the planet heats up and we keep in even more heat, that greenhouse effect becomes more effective, right? So now even less infrared light is coming out. We're trapping more and more heat. That means we melt ice, which causes, in particular, the ice at the polar caps, which causes sea levels to rise, creates more severe weather, okay? Because we have warmer oceans that can just put more energy into these large circular structures of storms. We have crop failures in zones where we used to be able to grow things because the climate's changed. So what we used to be able to grow in one latitude will no longer grow. Deserts will absolutely expand. We'll have a larger desertification across the planet. And we're going to have a spread of tropical diseases because things that could only survive in the tropics, many complex diseases, will be able to survive in what used to be temperate zones. Okay? All right, so enough about the atmosphere. Let's move on to what's going on inside of the planet. Well, seismic waves. All right, well, those are earthquakes. Okay, earthquakes produce both pressure and shear waves. Okay, this is an example of a pressure wave. This is like a slinky, and a shear wave is a wave that goes up and down. Okay, also known as a transverse wave. So earthquakes make both types of waves. Pressure waves are longitudinal. We talked about this term when we introduced waves. Okay, and they travel through both liquids and solids. Sound waves are an example of a longitudinal wave. Okay, shear waves, on the other hand, do not travel through liquids because liquids do not allow for shearing. You need a solid to get that restoring force from the shear wave. Okay, so liquids just don't resist it; they just move freely when you shear them. Right? Okay. So that means that you have two types of waves that are produced by earthquakes, one that does travel through liquids and one that doesn't. And this is very important for the study of earthquakes and the use of earthquake data to study the interior of the planet. Okay? So we can use that pattern of reflections from those two types of waves to deduce the interior structure. So imagine these scientists are collecting a whole bunch of data and they're actually mapping out the interior structure by where they see waves travel, because they know that the pressure and so P and S waves, so P are the pressure waves or the longitudinal waves, S waves are the shear waves, that both of those can travel freely through the solid mantle of the Earth, right? Here's the mantle. But only the pressure waves can travel through the core, both the outer core and the inner core. That's because the shear waves will not travel. They will simply get reflected off and pushed away from the core because they can't travel through liquids. And that then shows us the size of the core. Because look, as we map out these different locations where there are no S waves, we're then able to determine through calculation the actual diameter or radius of the core, both inner and outer core. Okay? All right, so the current accepted model is that we have a liquid core, right? And that's based on earthquake data. We never drilled down the hundreds of miles, thousands of miles. It's about 6,000 kilometers to get to the center of the Earth. Certainly we've never dug down there, but we're able to collect the data that strongly implies that we have a liquid core, okay? Furthermore, the mantle is much less dense than the core. So you might think, oh, liquids are less dense than solids, but not so when we're talking about liquid metal, which our core is made out of, okay? So our core is denser. The planet is differentiated with the densest material at the center. The mantle is rocky, the core is metallic, okay? So iron and nickel in the core, whereas the mantle is formed of lots of silicate rocks. The outer core is liquid. The inner core is actually so dense that it becomes a solid again. But again, those shear waves, the S waves, we never get to the inner core, but we can again deduce that based on the behavior of the P waves, the pressure waves, okay? The volcanic lava comes from the mantle, okay? So it pushes through the mantle, okay? And allows analysis of composition. Okay, so the mantle, solid and rocky, but has big structures of volcanic lava, which obviously is a liquid, right? But that liquid is pushing through cracks and forming huge structures within the mantle. Okay, so history of Earth's interior. So Earth was probably completely molten when it was formed. Okay, so as during the formation of the solar system, the creation of the planet, the whole planet would have been more like lava. Okay, but at some point it formed, remelted due to bombardment. So large, the couple 100 million years of bombardment, large meteors and comets crashing the planet, producing a huge amount of heat, keeping the surface in a more or less liquid state. Okay, but during that phase of almost complete liquid, that allowed for, just like we'd expect, heavier things to sink. So the heavy material over that liquid phase of the early planet sunk down into the core. All right. Now, radioactivity provides a continued source of heat in the core. So the core is still hot, still liquid, because all those heavy materials are associated with large atoms on the periodic table. Large atoms tend to have unstable nuclei, which means that they tend to undergo radioactive decay. As they undergo radioactive decay, they produce heat. Okay, and that's so important. We have a radioactive core to our planet, which is continuing to produce heat to this very day, despite the fact that it's been producing heat for 3 billion years. That's because it's a long, gradual process of heat production through radioactivity. Okay, so what is the deal with radioactivity and radioactive dating? Because it turns out we can date the age of rocks based on their activity level. Well, the number of protons in an atom's nucleus determines which element it is. That absolutely determines its number on the periodic table. However, there may be more different isotopes of the same element. So you can have different numbers of neutrons. Okay, so same number of protons, but different numbers of neutrons. That's what is considered an isotope. Okay, nothing to do with electrons. Electrons just determine if the element is ionized or not. Okay, many of these isotopes are unstable. Most isotopes are unstable, and they undergo radioactive decay. This decay is characterized by a half-life, because it turns out mathematically the probability of them decaying ends up having the following fraction of remaining original radioactive isotopes that will decay into the stable isotope. Okay, so the fraction of material remaining is 1/2, that's the half part, raised to the power of the amount of time that's passed over the half-life time. Okay, so what does this look like in practice? Well, consider a material that with a half-life that we'll just call the half-life. No particular value here. It could be 1,000 years. It could be 5,000 years, which is a common half-life for carbon. It could be millions of years, which are common, or billions of years, which are common half-lives for uranium. The important thing is if you have a sample of that material, after a certain amount of time of one half-life, you'll have 50% of that material left. It'll have changed into a different isotope. After 2 half-lives, you'll have 25% of that material. After 3 half-lives, you'll have 12.5, because each time you're just dividing by a half. As you continue, just keep dividing by a half. You never get down to 0, because there's so many atoms, you never functionally get down to 1 atom left. So you just keep dividing by a half, still having some fraction remaining. That's what we mean by radioactive decay and half-lives. Divide by half every half-life, which is a period of time. Okay? So half-lives have been measured in the laboratory for almost all known isotopes. Knowing these, we can use them to determine the age of a sample by looking at the isotope ratios. The most useful isotopes for dating rock are uranium-238, which has a half-life of 4.5 billion years. For radiometrically dating things like old bones, like archaeologists do, well, they're going to use a particular isotope of carbon, that I just mentioned a minute ago, has a half-life, I think, 5,700 years. But we're not talking about bones today. We're talking about rock. Okay. So the dating process involves measuring the ratio between the parent nucleus and the daughter nucleus. So that's the isotope that was radioactive, was unstable, and then the thing that it became is the daughter. That's the stable product. Okay? So lead-206 in the case of uranium-238. So uranium-238 becomes lead-206 when it decays. Okay? So we can see uranium-238, half-life of 4.5 billion years, becomes lead-206. So after exactly 4.5 billion years, a sample of uranium will then become half uranium-238 and half lead-206. See, that would be exactly one half-life. It becomes half of each. Okay? And then what would happen after two half-lives? Well, then you'd have 1/4 uranium-238 and 3/4 lead-206. See? Okay. All right. So let's move on to the surface of the planet. Continental drift. What's that? Well, that's all about plate tectonics and the resulting earthquakes when plates push against each other. So the entire Earth's surface is covered with crustal plates, which can move independent from one another. Very fascinating thing about our planet. At plate boundaries, we have earthquakes and volcanoes. Okay? So Earth's upper mantle near a plate boundary, we have an example of a subduction zone where one plate slides underneath another. That produces molten lava and a ridge of volcanoes as the lighter plate melts as it gets pushed down deeper into the planet. And as that plate melts, it becomes molten lava. That molten lava, being hot, rises up, much like hot air rises in the atmosphere, to bring it back to something we saw before. Okay? So a plate colliding with another can also rise it, resulting in very high mountains. Because sometimes one plate doesn't subduct under the other, the two plates just push into each other. A really dramatic example of that are the two plates pushing together that create the Himalayas. Plates can also slide along each other with no pushing, but just a sliding along. So we can have two plates here sliding side by side, North American plate or Pacific plate and North American plate, creating a fault line. All right, these produce a lot of earthquakes, these sliding plates. Okay, finally, plates can move away from each other because if they're sliding under each other, that must leave a gap somewhere. And it turns out that's because there's a few parts of the Earth where there's lava coming up through the mantle, pushing plates apart, creating a mid-ocean ridge. Shown here is the mid-Atlantic ridge, a very important ridge where basically new ocean plate is constantly being formed. Those ocean plates then get pushed away, and since ocean plates are less dense than the continental plates, they'll then subduct under the continental plates, like the South American and African continental plates. Okay, but that the continual production of new seafloor, new ocean plate is due to the Mid-Atlantic Ridge, which essentially is a ridge of small volcanoes. Okay, so the new crust created at the rift zones preserves the magnetic field. Okay, this is going to be a neat tie-in with something that we'll talk about in just a minute, the magnetosphere, because as the lava cools, it cools in a direction that points like a compass towards the North Pole. All right, because you have these basically magnetized molecules that are cooling and then cooling in that direction. All right, and what's so interesting is as we dig into the Mid-Atlantic Ridge, which has just been continually producing new lava, one layer on top of another for so long, we can actually see evidence of plate, or rather of magnetic field switching, field reversals. So it's really interesting. The magnetic field that allows a compass to point to the north, currently, it's something we absolutely take for granted in our daily lives, right? Although we may not use a compass in our daily lives, but we know there's a magnetic field. Well, it doesn't always point the same way. Every 500,000 years or so, the magnetic field switches. And it doesn't just do it instantaneously, it switches over a period of a few years to a few thousand years. And so, but then it's steady again for hundreds of thousands of years. So it's really interesting. We have this field that remains mostly steady, but every so often switches. Okay? All right. So plate motion, those plates that we kind of before were talking about how they can move relative to each other, but why do they move? Well, they're driven by convection. Okay? Because, again, like the atmosphere, hot material in the mantle rises, cooler material sinks, creating these convection cells, all right, of lava within the mantle. And that pushes the thin, very light crust around as the mantle does its convection zone movement driven by heat, okay? So if we follow continental drift backwards, we can see that the continents were all at one point formed together in Pangaea, and they have been splitting apart since, okay? And they'll continue to move over the next hundreds of millions of years, forming new continents and new supercontinents. It's just a continual process, all right? So if we have this record of the magnetic field in the mid-Atlantic crust or in the mid-Atlantic ridge, then that means that we should be talking about the magnetic field. And we'll talk about that as the magnetosphere. The magnetosphere is a region around the Earth where charged particles from the solar wind are trapped. Okay, so we have this magnetic field and it extends way beyond the Earth. As we can see, it's much larger than the planet itself, right? Hundreds of thousands of miles out into space. Okay, and as we look at that size of the magnetic field, we can see its evidence due to the charged particles that are produced by the sun. Because otherwise, these charged particles known as the solar wind, mostly electrons, they would just bombard Earth, they would hit Earth. But instead, they're redirected. They're curved due to the magnetic force of the magnetic field, because a charged particle, when it's in motion, experiences a force when it encounters a magnetic field. And that's exactly what is happening here with the charged particles coming from the sun encountering our magnetic field. All right, this causes the particles to get trapped within the magnetosphere. These charged particles are trapped in areas called the Van Allen belts, where they spiral around the magnetic field lines. They take helical paths, okay? And that's just due to the physics of the motion, all right? And those helical paths then follow the field lines, and where do the field lines go? To the poles. The field lines terminate at both the poles. That means these charged particles make their way down to the poles, forming aurora borealis, known as the northern lights or the southern lights. Okay? So that's the only time that the charged particles can even come close to the surface of Earth, are at the poles. And that's where we see that evidence of the solar wind. We see that evidence of our magnetic field directly. All right? So what about tides? Well, tides, having nothing to do with the magnetic field or Earth's interior, instead have to do with the interaction between our planet and our moon, because we have a very large moon, okay? And what happens is there's a gravitational force between Earth and the moon. And forces on the near side of Earth are greater than forces on the far side. That means that water can free flowly in response. The water gets pulled towards the moon on the side that is closer. The water also gets pulled towards the moon on the opposite side. All right, so actually notice the opposite side because it's quite interesting. On Earth's opposite side, the moon pulls at the surface. The moon's pull at the surface is weaker than at the center. Okay, and that's going to create a high tide on both sides of the planet when the moon is in this position. Okay, there's always a high tide on the side that is closest to the moon and the side that's furthest. Okay, you can also think of the fact that here the gravitational pull from the moon is so weak on this side that this causes the water to lag behind, creating a high tide, whereas the water on these sides gets pulled in this direction, creating a low tide. Okay? So there's always a low tide on the sides of the planet that are exactly perpendicular to the moon, and high tides on the two sides that are in a line. So that's why there's 2 high tides a day. Okay? Not just one. Okay? But in addition to there being high tides, we also have seasons of particularly high tides and seasons of particularly not high tides. And these are known as the neap tides and the spring tides. Okay? So when the moon is not lined up with the sun, this creates neap tides. These are ones that are where the high tides are not particularly high, the low tides are not particularly low. That's because the effect of the sun and the effect of the moon are canceling each other out. Now, the sun does not drive the tides as much, but as a contributing factor, it can hinder the effects of the tides. But when the moon and the sun are in a straight line with the Earth, well, then their effects are doubling up, and we have what are known as spring tides, which are extra high tides and extra low tides. Okay? Now, they don't actually occur in the spring, it's just the name. Okay, so tides tend to exert a drag force on the Earth, and they're actually slowing Earth's rotation. Okay, so over time, our day is getting longer and longer. Okay, it's only a tiny fraction of a second per year, but Earth is absolutely slowing, and the moon is drifting away, and that's due to the energy being lost to the tides. This process will continue forever until Earth eventually synchronously rotates with the moon. So that means that the same side of the Earth will always point towards the moon. Okay? That means that only one side of the Earth will actually see the moon. We won't see the moon rise and set anymore. There'll be one location on Earth where you can see the moon permanently in the sky. You won't be able to see it much during the day. It'll be kind of washed out by the sun. And then everywhere else on Earth, you won't be able to see the moon. And then you'll be like, really? When's that going to happen? Well, it actually won't happen for about 5 billion years. And it's going to, by the time it's completely synchronous like this, the sun will have already grown so large that it will have completely consumed Earth. So it never will truly happen unless something different, some different process happens with the sun. But if it wasn't for the Earth getting destroyed by the sun eventually, this would eventually happen. Okay? So let's summarize chapter 7. Earth's structure from inside to out includes the core, mantle, crust, hydrosphere, atmosphere, and finally the magnetosphere. The atmosphere is mostly nitrogen and oxygen, which thins rapidly with increasing altitude, although it does get warmer because of absorption of electromagnetic radiation. The greenhouse effect keeps Earth warm, right? Otherwise, it'd be too cold for there to be liquid water on the surface. The study of the interior of the planet is driven by measuring seismic waves. The crust is made of plates that move independently, known as plate tectonics. The movement at plate boundaries can cause earthquakes, volcanic activity, mountain ranges, and rifts. New crust forms at rifts show evidence of the magnetic field reversals. And Earth's magnetic field traps charged particles from the solar wind, which comes from the sun, then also forming the northern and southern lights. And finally, tides are caused by the gravitational effects of the moon and the sun. All right, well, thank you so much for watching this lecture. I hope it has been interesting and informative.